Alright, in this video we are going to review piecewise defined functions. And really the name is telling you exactly what's going on with your piecewise defined functions. They're just defined differently for different pieces of your function. So for different intervals of your domain, you have a different piece of your function. If we look at this example here, we see that f of x has really three definitions, right? And again, those definitions are kind of going to come into play on different pieces of the domain, right? So 2 plus x is only good when x is less than or equal to -2. My function is defined for -4 when x is in between -2 and 1, and it's defined to be x cubed when x is greater than or equal to 1. So on this example, we're just trying to evaluate our function at some different values. So if I'm looking at f evaluated at -3, the first thing we have to do is look at this value of x and see where it falls on these different intervals. So -3 would fall into this case right here, right? X is less than or equal to -2. So for that part of our function, we know my definition is going to be 2 plus x. So I'm really just looking at 2 plus -3, which would give me -1. If I'm looking at f of -2, again, I'm looking first at my function and seeing which definition of the function is going to fit when x is -2. Well, again, this first piece is when x is less than or equal to -2. So the definition of our function that we're using is this 2 plus x. So 2 plus -2 would give me a function value then of 0. So then we go to the next one. I'm looking at my function evaluated at 0. 0 would fall on this interval right here, right? 0 is in between -2 and 1, so I know my function is defined to be -4. If I look at f of 3, when x is equal to 3, my function would be defined to be x cubed, right? That's when x is greater than 1. 3 is definitely greater than 1, so my function would be x cubed or 3 cubed, which would give me 27. The last one then, f of 1, my function evaluated at 1. Well, this last definition when x was greater than or equal to 1. So again, it's falling under the x cubed definition, so 1 cubed would give me 1. Most of the time when we're dealing with piecewise defined functions, I think it's easier to look in terms of the graph. So the next two examples that we're going to do are graphing piecewise defined functions. This first one is the same function that we just evaluated for different values of x. Now we're trying to graph this. So as I'm trying to graph this, maybe the first thing that you want to do is again kind of think about those different intervals of x. So I know for this first one, x is defined to be 2 plus, or my function is defined to be 2 plus x when x is less than or equal to -2. So the other thing that I hope you recognize is that 2 plus x is a linear function, right? So here my y-intercept would be equal to 2, and my slope is equal to 1, right? The coefficient on x, if nothing is written there, we can think of that as a slope of 1. So if I just graph this function and kind of forgot about this limit on my domain for a little bit, I know again my y-intercept is 2, my slope is 1, so I would go up 1 over 1, or down 1 over 1, that's another point on my graph, and I could just connect the dots, right? This would be the graph of 2 plus x over the entire domain. The next thing I need to take into account or consider then is that this is only good when x is less than or equal to -2. So I notice if I plug -2 into this function, 2 plus -2 would give me 0, right? We can kind of see that's where my x-intercept is right there. And then I know since I'm only looking at my definition for the function when x is less than or equal to -2, I don't want any of this part of my graph when x is greater than 2, right? So I'm going to go ahead and erase the rest of that, and I'm just left with that portion of that linear function, right? Again, only when x is less than or equal to -2. Alright, so that's kind of that first one, and that's definitely an option as you're trying to graph these, is to just graph the entire graph and then limit it to the domain that you're looking at there. Alright, so then if we look at our second piece for our function, it's defined to be -4, and this is when x is in between -2 and 1. Alright, so if I look at just the equation y equals -4, hopefully you recognize this as a horizontal line. So I know the graph would look like a horizontal line at -4. Right? Again, if I looked at the entire graph, it would cover the entire real number line for x. But in this case, we're just limiting it from -2 to 1. And because these are strict inequalities, I know when x is equal to -2, I would have an open circle there. And when x is equal to 1, the same thing. I would have an open circle when x is -1. So it's really just that portion of the horizontal line between -2 and 1. Alright, so then the last part of our function is defined to be x cubed, and this is when x is greater than or equal to 1. If we look at x cubed, that was one of the basic functions graphs that we talked about. So again, hopefully you have an idea of what that graph looks like. And if we draw our x cubed graph, it kind of looks like this, right? So then we kind of say, okay, well that's the graph of x cubed for the entire domain. I'm only looking in this case when x is greater than or equal to 1. So since it's greater than or equal to 1, we would have a closed-in circle at 1, and then we could get rid of the rest of that part of that graph. That's the only piece that we're looking at for that part of my function. So I have a little bit of a cubic graph, a little bit of a horizontal line, and then a little bit of a line with a slope of 1. Alright, so if we do another example of a piecewise defined function where we're trying to graph, we can kind of do the same thing that we did in the last example, right? We're going to look at each one of these pieces on their little parts of the domain. So the first one is the absolute value of x, and this is good when x is less than -2. So my absolute value graph looks like a V. So I would know that would be what the entire graph looks like. But again, we need to restrict this. This is only going to be when x is less than -2. So at -2, I know I would need an open circle, and I wouldn't have any of the other graph to the right of -2. So we're just looking at that portion of it. If we look at the second piece, this is defined now to be x cubed when x is greater than or equal to -2 and less than 1. So again, this is that cubic that we saw in the last example. I know if x is equal to -2, -2 cubed would give me a -8, right? So a -2, 2, 3, 4, 5, 6, 7, 8. -2, -8 would be a closed-in circle. If x is equal to 1, 1 cubed is 1. So right at 1, 1, we would have an open circle, and we're connecting that with the shape of our cubic graph, right? So that's kind of what that piece then looks like as far as that portion of our graph. So then as we look at the last piece of this piecewise defined function, we're looking at the square root function, and this is when x is greater than or equal to 1. Well, if I plug 1 in, the square root of 1 is equal to 1. So even though we had a closed-in circle originally from our cubic, this square root function is going to fill that in and then continue with the shape of my square root function, which was another one of those basic graphs. So kind of putting that together, we really get a closed-in circle there at 1 and then get to continue again in that same manner of a square root function graph.